Hi, welcome to the 12th session on group theory, and this is the second session on cyclic groups and order of an element. Okay, so in the last session, we defined if an element A in a group is of finite order, then we define the notion of order of an element. And for that, we showed some important properties, namely, if A to the power m equal to identity, then the order of A, call it n divides m. And hence, as a corollary, we showed that if a to the power r equal to a to the power s, where r and s are integers, then r minus s is divisible by n. In terms of congruence, r is congruent to s mod n. The next thing we showed was, if order of a is n, then the elements identity a squared up to a to the power n minus 1, there are n elements, all of them are distinct. Okay, and that is also the cyclic subgroup generated by A. Therefore, order of A is nothing other than number of elements in the cyclic subgroup generated by A, right? So today we want to see what is the analog of that if the element is of infinite order. Okay, can you make a guess? What is the finite case? If a to the power m is identity, then n should divide m. But now we are saying a is of infinite order. That means for no n, a to the power n will be identity, right? That is the first statement. And what is the second statement? Yeah, there in the finite case is we said a to the power r equal to a to the power s. Then r is congruent to s mod n, right? But here in the case of infinite order, a to the power r equal to a to the power s, if and only if r equal to s. Okay, and what is the third one? If a is of infinite order, okay, then the cyclic subgroup generated by A consists of all a to the power n varies over z, and all the elements are distinct. That is, by it follows from the second one, a to the power r is not equal to a to the power s if r is not equal to s. Is that clear? This is the analog. So let us quickly state it and go ahead. Okay, so let me call it a theorem for okay, elements of infinite order. Okay, let G be a group. A in G. Okay, assume R of A is infinite. Then what is the first thing? The first thing you want to say is a to the power m equal to identity if and only if m is 0. Right? And second, a to the power r equal to a to the power s if and only if r equal to s. And third, okay, cyclic subgroup generated by A is nothing other than identity g squared g to the power n, keep on going. Here also you keep on going, g to the power minus 1, g to the power minus 2, g to the power minus m, and where m and n are positive. Okay, so all of them are easy. Okay, because if m is 0, of course by definition a to the power 0 is identity, and if a to the power m is e, notice that m may be negative, right? That would mean a to the power minus m is also identity, because a to the power m inverse is a to the power minus m, and this is identity, therefore that is identity. Now since m is negative, then minus m is a natural number, right? You understand? If m is not equal to 0, either m could be positive or m could be negative. If m is positive, it's already a contradiction, because there is a positive integer m, so that a to the power m equal to identity, then a is of finite order, but our assumption is a is of infinite order, therefore this cannot true. But suppose for m negative, that is m is positive, a to the power, okay, yet m is negative, a to the power m is identity, okay, m is negative, then I claim a to the power minus m is also identity. Why? Because a to the power m is identity, therefore the inverse of this is also identity, because it's e inverse, right? But our definition of a to the power m inverse is a to the power minus m, Okay, therefore that is identity. Now minus m is positive. Therefore that's a contradiction. Is it clear? So 1 is proved. Now what is 2? 2 is again the same thing. If suppose a to the power r equal to a to the power s, if r is not equal to s, let us assume, okay, if r equal to s, nothing. Okay, so assume r is not equal to s without loss of generality. Let us assume r is less than s. Then a to the power s, this is a repeated thing. Okay, this is equal to identity, right? Because multiplying both sides by a to the power minus r. Right? And now s minus r is a natural number because r is less than s, right? Therefore a is of finite order. This is a contradiction. Okay, therefore, okay, a to the power equal to a to the power s implies r equal to s. This way is of course obviously true. Third thing is also clear because all these elements a to the power n where is over z, all the elements are distinct by 2. Okay, and this also is the cyclic subgroup generated by 2. Therefore we have proved all the results. Pause, review, proceed. See, I kept my graphics tablet at a wrong place, so already my handwriting is bad. Now it's much worse. Is it okay? Right. Now let us assume that A is again here. Suppose I know order of A. What is order of A inverse? Okay. This again follows from the earlier argument. Suppose order of A, if A is infinite, suppose, okay, order of A is infinite, then we know cyclic subgroup generated by A is a to the power n different from z. All of them are, okay, a to the power 0 is identity, but all others are non-identity. Right? Okay. Is that clear? Yeah. Right. Now, I want to say these are equal. Okay. Why? If order of A is infinite, let us look at this is also equal to A inverse. Right? You understand? Right? Therefore, all of them are distinct. So, now suppose order of A is finite equal to n. Right? Then order of A to the power minus 1 to the power n is also identity because it is a to the power n, its inverse. Okay, but that is identity. Therefore order of A inverse is a divisor of n. But on the other hand, suppose order of A inverse is m, that means A inverse to the power m is identity, right? That means a to the power minus m is identity. That means a to the power, multiply both sides by a to the power m. Okay, a to the power m into a to the power minus m equal to a to the power m, and this is identity. Okay, therefore m is an identity, therefore n divides m. Right? Okay, therefore what have we shown? Order of A equal to order of A inverse. Make sure you understand this, don't get confused. Okay, don't assume such things. Are you following? Suppose order of A is n, then I want to prove order of A inverse is n. Right? So first thing is I will show that A inverse to the power n is by definition a to the power n inverse. Right? But this is identity because a to the power n is identity. Right? Therefore, if order of A inverse is m, then m divides n. Now I will show n divides m. Suppose A inverse to the power m is identity, that means a to the power minus m is identity. Multiplying both sides by a to the power m, I say a to the power m is identity. Therefore, n divides m. So earlier m divides n, and here I say n divides m, therefore m equal to n. Okay, good. So pause, review, proceed. Okay. Now let us look a lot more, some more things. Suppose order of A is equal to n, and D is a divisor of n. Right? Then I want to know what is order of A to the power D. Is the question clear? So, yeah, right. So let us try to understand this. Okay. Now suppose since d divides n, therefore n I can write as d times k. Right. Therefore, my guess is order of a to the power d must be k, because look at that, a to the d power k is a to the power dk, which is a to the power n, which is identity. Right. Therefore, let us say as this order is, let us scale m, and I say a d to the power k is identity, therefore m should divide k. Is that clear? Yeah. But notice that I am saying this m should divide k, but I claim, okay, m, therefore m is less than or equal to k, but I claim m must be k. Because why? Suppose my m is less than k, then what does it mean? A d to the power m is identity. That will mean a to the power dm is identity, right? But what is dm? Since m is less than k, dm is less than dk, but dk is less than n. You understand that? Therefore, a smaller power of a, okay, is identity. That's a contradiction to n being the order. Therefore, k equal to m. That means order of a to the power d is k, which is n by d. Okay. So understand this well. This is one of the very often used result. Okay. Now I can ask the next question. Okay. Suppose m is an integer. Let me again assume order of a is equal to n. And I want to know what is the order of a to the power m. Remember, in the cyclic subgroup generated by a, what are the elements? Are a to the power m, where m is over z. This may be finite, okay, because order of a is n, it's a finite, but let's not worry about. So whatever m you take, okay, I want to know what is it. Is the question clear? We had already worked out lot of examples in something like Z8, Z12, etc. Okay, please go through that. That will motivate this. I claim let D be the GCD of M and N. Yeah, right. Therefore, D divides N, right? Okay. Now I claim the cyclic subgroup generated by a to the power m is same as cyclic subgroup generated by a to the power d. This is a claim. Notice that a to the power m belong to a, right? Therefore, the subgroup generated by a, this will be contained in subgroup generated by this, and order of a is n. Therefore, order of a to the power m, number of elements in here should be less than or equal to this. Therefore, a to the power m is also of finite order. Okay, and we want to claim this. Okay, so let us do that. How do I do that? See, D is a GCD of M and N. Therefore, M I can write as D times R. Right? Therefore, you can see a to the power M is a to the power dr, which is a to the power d to the power r. Therefore, it belongs to the cyclic subgroup generated by a to the power d. Okay, is that okay? Next, remember, whenever GCD is involved, what result you have to use? Yesterday I repeated many times. We have to use the Bezo identity. So we will do that now. Okay. So since D is a GCD of M and N, there exists integers U and V, so that D is UM plus Vn. right? Now let's look at a to the power d then. A to the power d is a to the power um plus vn, that is a to the power um into a to the power vn, but this is a to the power m u by law of exponent. This is a to the power n b, but this is identity, therefore it is a to the power mu. Therefore ad is belong to the cyclic subgroup generated by a. Yeah, you understand? Therefore the cyclic subgroup generated by ad is contained in cyclic subgroup generated by am, but that is contained in cyclic subgroup generated by ad. Okay, therefore am belong to this, that means the cyclic group generated by am is contained in cyclic subgroup generated by a2. This is 1 and this is 2. Therefore we have proved our result. The cyclic subgroup generated by a to the power m is same as cyclic subgroup generated by d. What is d? D is the GCD of m and n. Now what is the therefore what is the order of a to the power d? We already saw if d is a divisor, because remember it's a divisor of n. Therefore this divisor is the order is n by k. Therefore order of a to the power m is n by k, that is order of a divided by GCD of m and n. Pause, review, proceed. So do you see that? So we proved very interesting results now. What is that? Assume that A is of finite order n, then if D is any divisor, then the order of A to the power D is n by D, because that's an integer, because D is a divisor. Next thing is, start with any integer m, then order of A to the power m we know. We can compute it in terms of order of A. How did you do that? It is order of A divided by GCD of m and n. Very beautiful result. Now there is something very interesting from this. Okay, what is that? Let us look at it. I hope I did. Yeah, right. Okay, in particular, suppose I may want to know when this is equal to a to the power k. Right? Remember, a to the power k is here for any k integer. Right? In particular, let us say k is a natural number. This has to be in a. Therefore, this is always contained in this. What I am asking is the other way inclusion. Right? If this is true, suppose this, that means a must be in this is a to the power k. Yeah, but what is the order of a to the power k? Order of a to the power k is order of a divided by GCD of m and n. Sorry, k and n. Would you follow that? Yes. Order of this is, yeah, okay. Now let us see. Since a belong to this, what does that mean? That means there exists an m such that a to the power k power m is a. What does that mean? A to the power km equal to a. That means a to the power 1 minus km is identity. Right? Now remember, order of a is n and a to the power some integer is equal to identity. Then we know it is 1 minus km should be divisible by n. Right? Therefore 1 minus km should be a multiple of, let us say, r times n. That means 1 equal to km plus rn. Right? So if you want, let me write it the same way, mk plus Rn. That means GCD of K and N is 1. Okay, so what have you proved? We have proved if a to the power k is same, that is same as saying order of a to the power k is order of a, that is equal to n, implies okay GCD of k and n must be 1. Conversely, pause, review, proceed. Converse is also true, right? If GCD of k and n is equal to 1, then I can write uk plus vn equal to 1, right? Yeah. Therefore, let us look at, so the yet raise it to the power a equal to a k to the power u plus a n to the power v, sorry, times, which is a k to the power u. That means a belongs to the cyclic group generated by a to the power k. Yeah, right? And since therefore cyclic subgroup generated by a is contained in cyclic subgroup generated by a power k, but that's already contained in cyclic. Therefore, these two are equal. And hence, the number of elements here is same as number of elements here. That means the order of A equal to order of A power k. So, what do we have proved? In fact, this one I could have done from the earlier one. In fact, I started with the true, but then I decided not to do it because I wanted to illustrate why Bezo identity is very, very useful all the time. Okay, whenever you talk about GCD or relatively prime, okay, then you should always think of Bezo identity. Okay, right. So, what are the things so far we have proved? If D is a divisor of n, let A be a group element whose order is n. If D is a divisor of n, a to the power D, order of that is n by k, n by d. Okay, number one. Next, if a to the power m, okay, for m is an integer, what is order of a to the power m? That is order of a divided by GCD of m and n. The next thing, when does a k generate a? That is order of a to the power k is same as order of a, right? It is same as saying, look at the cyclic subgroup generated by a. When does a power k generates the same cyclic group? That is, it's a generator of the cyclic group a. If and only if k is relatively prime to n, which is the order of a. Okay, please go through these things. They are all very, very easy results, but very, very powerful. So don't get confused. Revise it at least once or twice. Okay. Now, so we are ready to prove the basic results on cyclic groups. Okay. So let G be a cyclic group. One, if G is of infinite cyclic group, that is, if G equal to A and order of A is infinity, then the only generators are A and A inverse. Okay, and so let G be a finite cyclic group. So let G equal to A and such that order of A equal to n, that is the number of elements in G. Okay, then what are the things we show? Okay, these are the points we are proving that A, okay, for every divisor D of n, there exists a subgroup of order D. Maybe I will write it as K because we used K, order K. Okay. How do you do that? So, if K is a divisor, write n equal to K times D, right? Then let us look at a to the power D. Then D is a divisor of n, and we have seen order of a to the power D is order of n by D, which is K, right? Therefore, what the number of elements in this is same as order of a to the power D, and hence is equal to K. Therefore, for every divisor of n, there is a subgroup of order K, right? The next thing we want to show is something interesting. B, for every divisor D, for every divisor, say K of n, there exists a unique subgroup of order K, right? Yeah. Before that, yeah, there is one, the most important thing I forgot. Okay, let me come to that. The first result, I would say, forget this, call this as B. Okay, there is the first result which I forgot. That is, if G is cyclic, okay, any subgroup H of G is cyclic group. So this may be a cyclic group which is infinite or finite. So sorry for the goofing. Let me state this as a separate theorem. Let G be a cyclic group. That means it could be finite or infinite. Let H be a subgroup. Subgroup of G. Then H is cyclic. So let us prove this. Do you see that we have seen something very similar in the additive group of integers? We found out all subgroups. We found they are all of the form some a times z. That is multiples of a, right? That means each one of them is cyclic, right? Do you understand? Because it's a subgroup generated by a. Now, how did we find that a? Do you recall? The same trick is what we are going to do here. The way we found out that a in the additive group of integers is assume the subgroup is non-zero, then there is a non-zero element, okay? Therefore, a or minus a, okay? One of them must be positive. We assume a is positive. Therefore, the set of positive elements in the subgroup H is non-empty. By well-ordering principle, there is a least element. Call it A. That A is the generator. How did you prove? Using division algorithm. Exactly the same proof goes through here. Okay. Let us go through the proof. Okay. Okay. If H is identity, then H is the subgroup generated by E. Therefore, cyclic. Right? So, assume H is not equal to identity. Therefore, there is an A in H, right, which is not identity. Right? Okay. Now, let us look at, sorry, so sorry. Oh, sorry, let me again. So, let us start with let G equal to A. Okay. You understand that? Okay. Yeah. Let A be a generator of G. Let G equal to cyclic, right? Now let H be a subgroup of G. If H is the subgroup, identity subgroup, then it is singleton identity. Then H is the subgroup generated by E. Therefore, it's cyclic, right? Therefore, I may assume H is not equal to identity, right? That means there exists some power of m, okay, there is an integer m not equal to 0, so that a to the power m belong to h. Is that clear? Yeah, right. Now m is non-zero, therefore m could be negative, but then since this is a, this implies a to the power minus m also belong to h. Therefore one of them m or minus 1, exactly one of them is positive. That is a natural number. You understand? Therefore if I denote by the set S, set of, okay, k in n, so that a to the power k belongs to the subgroup h, this is not empty, because either m or minus m is an element of this. Is that clear? Therefore this is a non-empty subset of natural numbers. This is contained in n. Therefore by well ordering principle, okay, there exists a least, okay, okay, I can simply say least n, okay, least n, a natural number, such that a to the power n belong to h. Is that clear? Please compare this with exactly the same thing. Z under addition, h is non-zero, therefore there exists an m non-zero number integer which is in h, therefore I can assume m is positive, right? And let n be the least element such that n belong to h, least positive integer such that belong. What we want to prove? We want to prove my h is a to the power cyclic group generated by a power n. This is what we want to claim. Alright, the proof again proceeds the same way. First notice that this is contained in h. Yeah, right. So I want to say any element, suppose a to the power m belong to h, then I want to say n divides m. Therefore everything in h is a multiple of m, multiple of n. Do you understand that? Okay, remember h is a subgroup of this, therefore all elements of h are of the form a to the power m. I want to say a to the power h equal to the cyclic subgroup. That means, okay, any element a to the power m should be of the form a to the power n to the power k, because cyclic subgroup generated by a to the power n, how do they look like? A power n to the power k, where k varies over z. So I have to prove that way. Is that clear? That means I have to prove n divides m. So what do you think I should use now? Right? Division algorithm, obviously, right? So let us use it. So let a to the power m belong to h. By division algorithm, I can write m equal to q times n plus r, 0 less than or equal to r less than n. So we want to claim r is 0. That's all. Now notice that, okay, a to the power n belong to h. Therefore a to the power n power h also belong to h. By assumption, a to the power m belong to h, right? Therefore a to the power minus nq also belong to h. A to the power nq, this is a to the power nq belong to h. Therefore a to the, its inverse is a to the power minus nq, that also belongs to h. And a to the power m belong to h. Therefore a to the power r, which is a to the power m into a to the power minus nq, belong to h, right? If r is not 0, if r is not 0, then r is a natural number which is strictly less than n, and such that a to the power n belong, a to the power r belong to h. But that this, okay, if r is not 0, this is a contradiction. Because r is a natural number and r is strictly less than n, but a to the power r is in h. But what is our choice of n? N is the least positive integer such that a to the power n is in h. Okay, therefore r has to be 0. That means what? M is q times n. Therefore, if a to the power m belong to h, then yeah, n divides m. Right? Therefore, a to the power m is of the form a to the power nq, which show that it is in a to the power n. But this is an arbitrary element of h, therefore h is contained in this. But a to the power n belong to h, therefore it is equal to h, therefore equality holds. So, you can see the proof is exactly similar to the classification of all subgroups of Z. We found all of them are cyclic. Now we are proving a very general case. Give me any cyclic group, maybe finite, infinite, I don't care. But every subgroup is cyclic. Okay. What is a generator? Generator is look for the, if H is not identity subgroup, then look for the smallest natural number n such that a to the power n belongs to H. Then that a to the power n generates H. That's what we proved. Is that idea clear? Very good. Okay. Now I think I can go back to the all the basic results about cyclic groups. I forgot to mention this. Okay. Let's go through back. So the fundamental theorem or basic theorem, fundamental theorem of cyclic groups. Okay. The first thing is, oh, let me see whether I made it. See, good. I forgot. Okay. What is it? Let G be a cyclic group. The first one, any subgroup of G is cyclic. Okay, that's what we just now proved. And second, let G be a finite cyclic group. Then for every divisor D of, let us say, of order n. Okay. Okay. For every divisor, since n, there exists a unique subgroup H, so that mod H, that is the number of elements in H is D. Right? So one is already proved. Already proved. Let us prove two. So let G be a cyclic group of order n. Say G equal to A, order of A equal to n. Then we want to say there is a unique subgroup. Okay, let D be a divisor of n. Then I can write n equal to dk. Right? Now let's look at a to the power k. Okay, what is the order of a to the power k? Okay, that we already know, it is nothing other than d. Because if you remember, it is n divided by GCD of n and k. Yeah, since k divides, it is again n by k. This GCD of n and k is a divisor of n, therefore it is GCD is n itself. But that is, yeah, sorry, k itself. Yeah, okay, therefore it's d. Right? And therefore order of this is d. Okay, therefore the subgroup, okay, this subgroup has d elements. Therefore what have we shown? There exists at least one group, one subgroup, one cyclic subgroup, but any subgroup has to be cyclic. Okay, any subgroup of order having d elements. Right? Next we want to show, is it unique? So let H be a subgroup of G such that order of H equal to D. Then I want to prove, we want to prove H is nothing other than A to the power K, the subgroup which you already found out. Is that clear? Now how do I prove that? Since H is a subgroup of G, H is also cyclic and G is a subgroup powers of A, therefore H must be A to the power M. There is an integer M such that H must be A to the power M. Right? Right. Now order of H equal to D implies order of A to the power M must be equal to D. That implies A to the power M power D must be identity. That is A to the power MD must be identity. But remember, order of A is N and order of MD is also identity. That means N must divide MD. But what is N? N is KD. Therefore, KD divides MD. Since D is non-zero, that means K divides M. Yeah. Since K divides M, that means A to the power M is a power of A to the power K. Right. This belongs to the subgroup generated by A to the power K. Right. But right. So A to the power M belongs to A to the power K. Therefore, the subgroup generated by A to the power M should be contained in the subgroup generated by A to the power K. Right? This is a subset. Right? But this is nothing other than H, therefore this has D elements. This also has D elements. Okay, a subset, okay, has the same number of elements as the full set. That means these two sets are the same. That means the subgroup H is nothing other than A to the power K. Okay, pause, review, proceed. Oh, okay, I'm sorry for that goofing. This since I got the phone call, I was sidetracked and I lost my focus. Okay, without sharing the screen, I completed the proof, but for your sake, I again share the screen and complete the proof. So we have proved all the results which you will need about order of an element and cyclic groups. Please go through that. As you can see, many of the things are intermingled. Okay, and all the facts which I proved, some of them are not even done very specifically. It is as a part of a theorem, the general theorem, the last fundamental theorem of cyclic groups, they are done. For example, order of A to the power M, we found it is nothing other than N by GCD of M and N. Okay, that is actually part of the proof, but we already made it a separate thing. These kinds of things are very important. Please go through it. And again, my advice, don't try to remember anything. Try to go through the logic, understand, you begin to think the algebraic way. That is more important. Okay, you will slowly see that you will be able to generate all the proofs on your own. Yeah, you don't have to remember. Okay, it's possible. Okay, have confidence in yourself. Okay, I hope you enjoyed the lecture. We will meet again. Take care. Bye.